All right, we are going to repeat again and again and again how to draw the mechanism because it's really important. We're going to start with the full reaction mechanism of an SN1 reaction. All right, we'll do it together right here. And for you, just draw the mechanism. Just follow with me. All right. If you have the handout, you should have most of this already, all the structure, and just ready to draw the mechanism. All right, a typical SN1 reaction, you should see two steps: a carbocation formation, which is the first step, come up first, and then nucleophilic attack. All right, so stick with this too. This is like there's a mechanism, a typical mechanism of an SN1 reaction. There might be some additional steps that you have to do, but we'll talk about it later. All right, so what we got? We have tertiary alkyl halide, alkyl iodide, and your nucleophile is a bromide. All right, so bromide will replace iodine. All right, so first step is a carbocation formation. So leaving group leaves, you get a carbocation. And to remind you one more time, I said it many times, carbocation is flat and it got an empty p orbital, so there's space at the front and space at the back. Bromide can attack on both sides, so you get two products there, one at the front, the other one from the back. All right, so this is a typical SN1 reaction mechanism. Now, there could be additional steps, all right? For example, proton transfer at the end, all right? But one thing though, I don't want you to memorize, oh, there's going to be proton transfer at the end. There might be proton transfer at the beginning. There may be proton transfer in between carbocation and nucleophilic attack. No, don't memorize that. I want you to play it by ears. When you draw the mechanism and say, hey, I need to do something on it. What can I do? And we go from there, all right? I'm going to show you right here. Let's say I'm going to forget about this. I know this is going to be an SN1 reaction. Okay. And now, basics SN1 reaction, two-step carbocation formation and followed by nucleophilic attack. Oh, let's see what happened. Leaving group leaves, you get carbocation. Now, ethanol go attack right there. All right. So you should get this species. So oxygen, neutral oxygen become positively charged oxygen. All right. I note a little bit here. So I use a squiggly line, which mean which mean wedge line and dash line. So what it means is instead of drawing two structure, now you should get two enantiomers here, a pair of enantiomers. Instead of drawing two structures, I can use squiggly line, which mean both enantiomers. You can do that. Or you can draw one and plus E. E stands for enantiomer, also works. So it saves you some time of drawing. Okay. All right. So use squiggly line, so you get two products here. But we're not done yet. All right, so I want you to see charged compound, not stable for sure. And from this point, it requires additional step to make this guy neutral. Why do I do that? Here's the reason. Are you familiar with this acid? Hydronium ion. You guys know this is a strong acid, is it? Right? This is a strong acid. What does a strong acid do in a solution? They dissociate, right? So they won't stay as hydronium ion. It dissociates. So one proton leaves, become water. That's much more stable. All right. So same thing, look just alike. So oxygen with 3 bonds here, oxygen with 3 bonds. So this proton is really acidic. How acidic? About negative 1.7. About that. Okay, so this proton is going to leave and a base is going to come grab it, which is a solvent. We have a lot of this nucleophile floating around because ethanol also acts as a solvent. All right, so we have a lot of this. One of these is going to go grab a proton transfer, and to make a neutral product. And that's what you should get most of the time you draw a mechanism. You should get a neutral product there. Your product should not stay as a highly acidic compound. All right. If it's acidic, acidic compound like hydrochloric acid, sulfuric acid, it won't stay as an acidic compound, acidic form. So they dissociate, become conjugate base, which is much more stable. Okay. So this looks like water. It has oxygen with two bonds, oxygen with 2 bonds. It looks like water. All right. So proton transfer at the end. Sometimes you will see this. All right. Or, let's concept test real quick. So from here, if this were to be your nucleophile, you're going to draw the SN1 mechanism. Which one require proton transfer? That's a trick that you can guess, right? I go back right here real quick. So if you see this reaction, this is an SN1 reaction. If you see the nucleophile, it will give you a hint that, oh, you have to do proton transfer at the end. But how do you know? Well, if you see a neutral nucleophile, that's when you have to do a proton transfer at the end. And here's the reason why. Look at A. The nucleophile is not neutral. Sulfide is sulfur minus. A negatively charged nucleophile attack become neutral. So the charge lower by 1, right? Decreases by 1. But if you started with a neutral nucleophile, which is in B, sulfide, dihydrogen sulfide, which is a neutral. After nucleophilic attack, it will become positively charged. Every attack, the charge of the nucleophile goes up by 1. Negative go to 0, neutral. Neutral 0 go to +1. See that? So it tells you if you see a neutral nucleophile, it gives you a hint that at the end you have to do a proton transfer because right here a positively charged compound is a strong acid, usually a strong acid. The base anywhere in the solution will come grab a proton right away. Okay, so who else require proton transfer at the end? C for sure. If you start with water, if water attack, you're gonna get something look like hydronium ion, which is look just like this with the oxygen in the middle, hydronium ion, and you know that's a strong acid. Will require another additional step of proton transfer. Ethanol also a neutral, just like water, oxygen with two bonds. See that? When this guy undergoes nucleophilic attack, it will become positively charged. So similar looks, the structure will look similar to hydronium ion again, and you have to do the proton transfer at the end. So yes, cyanide ion, negative charge there. Nucleophilic attack, you're gonna get just cyanide, Cn, neutral. So that's good. We don't have to do proton transfer at the end. Chloride attack, this is chloride Cl minus. When it attacks, just like this, right? You're gonna get chlorine, neutral chlorine. So you don't have to do anything about it. All right. Let's moving on to the another mechanism.